So hello everyone, I hope you can hear me. Please let me know that you can hear me in the YouTube chat because today we're gonna communicate primarily through the YouTube chat, not the Google Classroom, because everybody is at the same place at YouTube Live. Like normally it'd be better to have at least some part of the class in the person where I can come and help with the code directly, but now we will be all joining in here at YouTube. So please let me know in the YouTube chat. Can you hear and see? Plus, minus. If there is any problem, let me know. Otherwise, please engage with the chat in YouTube. And we will also, of course, submit a lot of work inside the Google Classroom. Thanks for some answers here. So in Google Classroom today, we're going to work with a few tasks, and so the one of the first tasks will be 5.2. That will be the regression task in Pytorch, and now today we're going to work a lot with Pytorch, and next week again. Next week I think is the last session in this small mini course in deep learning, and next week the Pytorch, you will see what you can do even more with the power of Pytorch, with the way how to construct the deep learning function graphs and make them more like usable, you know. So first of all, please get inside the Google Classroom and get the template. So I just noticed that there is maybe some problem with the link there, but the template link works. So and I've just now a little bit cleaned it up. So let me show you what I mean. So you should go in the Google Classroom, find 5.2 task, download from this link the template for your code. So, and then we will start. So please let me know if the 5.2 template is ready. So 5.2 template ready for work, plus minus. If any problem, let me know in the chat. Then I will go through the step by step through the template. Again, today we're gonna work with Indian used car dataset. So this is like ss.lv in Latvian used car datasets, you know. But I have not yet scraped ssl.lv. If somebody has done that, so that then somebody could give me the dataset and then we can play with that. But yeah, well, so the idea is that we have all sorts of old car, maybe not always old, but just used cars, and for those used cars, depending on the features of those cars, we want to predict the price of the car, right? So if the car is turned manual or automatic, and if it's made in 2008 or 2002 or so on, and what is the brand? Is it BMW, or is it some Audi or anything? So, and then we predict the price, right? So that's the task for today. And I'm just waiting for you to confirm that you have the template 5.2 ready for work. You just download it from the link from the Google Classroom. And also I dropped it also here in the YouTube description, and also in the YouTube chat. So just pick that template, and then we will start working with it. We'll do some things together, then you will do a few things, then we do again some things together. And today the plan is that we will work with pure Pytorch in the regression task and then classification task. Okay, I see 1+ coming in. Meanwhile, while we're waiting, here I have some nice chart. This is kind of I think very telling for the reality of the deep learning research and the actual production use. So this is just why we are focusing on the PyTorch. So of course, the first like major library that was after the MATLAB that dealt with deep learning frameworks, that was TensorFlow, the yellow one. And in the very early days, like 2010s and then up to like 2016, the TensorFlow was kind of leading libraries. The Google supported it. It grew, and then at some point, because it was built on Python, there was better ways how to do the function graphs in Python using so for the deep learning. And then LeCun and I think, I'm not sure if LeCun was the first one, but basically Facebook started using the PyTorch, and then they developed it, and then a lot of researchers started using it. And now if you see that the GitHub implementations and also the papers and also production use, so for the PyTorch, this is like kind of the main most powerful library that we can use for the deep learning research and also for the production. There are very big advantages over TensorFlow, where you can debug your function graphs in real time at any point in the graph without like sacrificing a lot of other things. Then that's one of the big things. Then of course all of the functional parts are still implemented in C, C++. You can easily move from different platforms. So it's kind of the main go-to library right now. Okay, so and they are also thinking about creating TensorFlow 3. I have not yet checked what was the status of that, because TensorFlow 2 was a little bit of failure, and TensorFlow 1 was basically the old thing. So the TensorFlow is the idea that you first create a graph, then you compile it, then you use it. But I think they had plans for TensorFlow 3 on Swift language, so I will check if that's still the case. Swift for TensorFlow. So they want to compile it. So I'm just saying that there might be some changes in future, but now the Pytorch is kind of the main library. TensorFlow 3.0. Not sure. Not sure what's happening with that, and have not yet checked that. So if somebody has interesting information on that, you can share that. Okay, anyway, so I see only 3 people ready for work, but we are 10 people online. So let's wait for a little bit more. It's kind of strange that you're not ready to work. So, I mean, like, you just go inside the Google Classroom, pick this template link. You see there is a link here, this one. And then open the link in the your PyTorch PyCharm environment, sorry, PyCharm environment, or Google Colab, or any place where you can work with it, you know. So you have options: Google Colab or PyCharm, or maybe even Visual Studio Code. Well, like, I think that was the name. So any Python editor, right? So please open that so we can start working with it. So I see only 4 people confirming. We need to wait, I guess, a little bit more, but we cannot just sit around forever. So wait a few minutes more. right? So if you have configured your, oh man, potential risk. So the Python file, of course, is a script file, right? So you can do the programming in Python file. Of course, this is a risk, right? This is not no virus, of course. This is just like the file where you can do programming, and somebody can mess around with your computer if you don't understand what you're doing, you know. So, anyways, that's the. Thank you for letting me know that there might be problems of downloading the file because the browser thinks that you don't understand what you're doing. So anyways, yeah, if you get the warning that the file contains something dangerous, then just ignore and download, because that is simple text file with nothing else than the pure code inside there. So this is what we have here, right? So this is would be now all the time in our course. So anyways, so here we have the Pytorch. That's crazy. So maybe I should then later for the next tasks always zip the files so that the Chrome would not think that you don't understand what you're doing. So anyways, okay, so here let's see what we have. We have the dataset of those car dataset, right? So the only thing that I changed here is that I cut out the first 4 dimensions of x and split them in separate vector, which is called x classes, which are the categorical parts of the inputs. So what I mean by categorical parts of the inputs, maybe we should add some breakpoint and show you what's inside there. So I will run this. So the categorical parts are those parts which are not scalar values. Of course, like the production year, like 2009, 2010, whatever, those are scalar values, but we have also categorical values. So you see, I have here these things. So if we look at x, so the x first row, we have the car. So if you start looking from the far right side, so the car had 1 owner before. The car was run for 20,000 kilometers, I think, or miles. Then 2018 it was produced, so probably those are kilometers. Then there are 4 like scalar values. So the 0, let's see what the first 0 actually means. So self labels. So here we have the labels, and so the last 0 from that side after the 2018, it means that the car is individually sold. It's not a dealership. Then the next one, 0, means it's a manual car. Then the next 0 means that this is a diesel car. And then the last, the 7 means the brand of the car. So that's, let's see, this is a 6. So the 0 is the first category. So it's Mahindra. So anyways, some kind of interesting car brand from India. There is also Renault, Ford, Toyota, whatever. So anyways, those are the categorical parts of the inputs. We will look at that a little bit later, but the idea is that it's not just like some kind of fluid scalar value. It's not going from like 2000 whatever and 2021 for the production. It's actually some kind of classes category. So that's why I split it out. So the X classes, it's one part which is split out. So you don't care about that right now. It's just that we have 3 outputs. We have the X, we have the X classes, and we have the Y, which is the price of the car, right? So also you notice that the data set now is not get from the object, it's get from the Torch utils data set, right? So that's a major thing as well. So everything which is inherited from Torch type of libraries behave like a like a torch type of objects. So this is very important to notice that this is not just a simple object. Then if you have a dataset which is inherited from Torch dataset, then you can do all sorts of interesting things. So one thing is you can use Torch utils data, which will provide you with the ability to randomly split the dataset in two parts for the training part and testing part. So in this case, we lock the seed. So every time when we run this same code, it will always be split in the same parts of dataset. So 80-20 or 70-30 percent split or whatever. So, and then we have the Torch utils data loader, which is exactly the same as we did with NumPy. All of the things that we previously did with NumPy are almost one-to-one to what you see here. It's just that now a lot of things are much more automated because they are done automatically in the Pytorch side. It's already implemented, so we don't need to implement them. We know how it works. So here the data loader, which is what it does, it takes dataset and puts together a mini batches of size, for example, 16. So I take 16 samples from my dataset, 16 cars, put them together, and then pass all of those 16 cars inside our model in this functional graph and get out the prediction, right? So, and here for the training, we have also option to shuffle training dataset every time when we run it. And for the test dataset, it might be not non-shuffled, so we can compare them in between epochs. Then we have the module part. So for the module part, this is what we will implement now. So before we created all of our like layers and models as an object classes. Now these will be Torch NN module classes. Torch NN module classes means that it will have some automatic functions that will improve the way how we can build the models, will allow us to make them much more complicated and allow us to not worry about some parts of the models. So this will be the first part that we will build, and I will help you out how to build it. There will be actually two parts of the building model. First, we will ignore the X classes. We'll make it as you did it in the homework. And then afterwards, we will add the X classes as well. And then we will move to also to the classification task at the end of this session, which will not be a huge jump from what we already will be doing so far. So, okay, so let's look then at the model. So for the model, we have forward. Remember in your NumPy models, you also had the forward and backward. This is the same idea, exactly the same idea. So here, initially in constructor, we want to define which will be the learnable parameters, right? If you remember that learnable parameters always live in linear layer, and there are weights and biases. There are also some other types of functions where you can have learnable parameters, but now let's focus on what we know already. So what we will do is we will create the self layers. Self layers. If you have any questions, ask them in the chat. And here before, like in before days, what we did just create a list. But now we will create this as a torch NN sequential, or it can be also torch NN module list or anything like that. So the idea is that if you would create this as a list there, everything will work fine, except you will need to also create your own function for the parameters, def parameters. Remember we had this function, parameters. So if you would like to create your layers as a simple Python list, then you also need to create the parameters function where you select which parameters are learnable, because in this case, the torch and sequential already have that function included, which selects the parameters which are learnable. That's why this is more convenient to use. So here, let's say, so we have torch and n linear. So this will be linear layer, exactly as we made it before. And the in features will be the how many features of a vector we have as an input for those car descriptions. And initially, if we ignore X classes, then we have only 3 types of features. So the production year, the mileage, and how many owners the car had. So this is 3 input features. Then out features, remember the idea that what we want to kind of like compress the features, or maybe it's sometimes useful to expand and then compress, but we could go by compressing it now as well. I see that somebody is still getting problems with downloading simple file. So what else can I help you out with the file downloading? If you would be on Linux or Unix, then you could do that from console, but in Windows, it's really terrible. So anyway, I really hope that you managed to download that file somehow. Um, uh, Let me check. Maybe there is a command line for Windows as well. Windows, we get command line. How do you do that on Windows? Windows 10 includes the CURL. Yeah, seems like it's including that. So it seems that in Windows, in command line, you can download files without like stupid kind of error messages with something like this. I will show you the command line. If anyone has again problems downloading simple files from internet in Windows, then you can try out something like this. So I'll drop maybe this line in the Jamboard. If you have still problems downloading files on Windows, then please let me know in the chat. So otherwise, I'm just now showing the code and you're not even ready to work. So here the idea is that you use in your command line curl.exe, then output, or maybe even it will work without output. It should probably work if you just cd to your downloads directory and then download it just like that with the link that is given already in the Google Classroom, and then it should just download that file in the current directory. So if you have any problems with kind of all sorts of strange stuff with Windows, you can try to download using that. So anyway, we need to return to the code. I really hope that most of you managed to download like simple text file. So anyways, here it's just a text file. We don't understand why there's problems. So anyway, here let's say then the out features we can stay as the same as 3 and then reduce them a little bit. So it will just give the same kind of projection on different scale. So then here let's say torch and n sigmoid function, non-linearity. Remember, we are using non-linearity functions. So that if we would add just all of the linear layers one by one, at the end we would get the reduced to some common linear projection, which is non-usable in most cases. So then the kind of the non-linearities help us to make the space divided in more interesting ways to kind of extract out the external, like some kind of hyperdimensions, and then do the linear projection. So we will do this. Then let's reduce the features down to 2 features. It will be kind of like slow compression, right? So, and then at the end, the in features will be 2, and then out features will be 1, which is the car price. So we will want to predict the car price, right? So that's one. And then in the forward pass, it's very simple. So y prim, this is the prediction price, right? So this will be the self layers forward of x, and the output is y prim. And the good news with the Pytorch is that we don't need to write the backward pass. We could, in Pytorch, the backward works, so we could implement the backward function as well. So the custom gradient, custom derivative of our function models, but it makes automatic derivation. So remember that the partial derivatives, the derivatives that we calculated by hand, they are just very, very simple formulas that you take from the table one by one and chain them together using chain rule. So what it means is that you can automate that process, and the same way as like in Wolfram Alpha, the TensorFlow, also in the Pytorch, so that the auto derivation engine is included. So you can write all of your functions just in one way, and they will automatically work in another way. So they will automatically find the gradients, the derivatives, and then you can use them to do the SGD, or stochastic gradient descent. So we have the model ready. So I will drop the model to the Jamboard so you can catch up with it. So the model will be on slide number 3. And I will wait for you to confirm that you're ready to work. So is model ready? Plus, minus, if you have some errors, problems, let me know. So right now, you should not start running the code because we are missing a lot of parts below, but it's just that this part of the code should be ready, and then we move on to the next part. So I'll wait for your confirmation, and then we will move on. So I see 5 pluses coming in. That's great. Okay, so let's move on. Then the next part of the code will be new custom loss function. So remember that you had for the home to create, I think, L2 loss function, right? So now we will implement the Huber loss. We will explain briefly what it is just in a second. So let's jump for a while on the Jamboard here. So let's go to slide number 4. The loss function that I want you to implement is following, and we will do this together, no worries. So this is the equation. So remember that the mean square error and the absolute error, right, they have different kind of properties, and there are a lot of loss functions. You can create your own loss functions. So the loss functions are a really useful thing what to work with. So this is a very powerful part of the deep learning models. For example, here we have an example that so if we had a data set with the cars, right, and then we want to predict the price of the car, and if the data set is noisy, if there are somebody entered the wrong prices of the cars, right, then in that case, if the dataset is noisy, then the wrong car price will result in large loss, large error, right? So if the error is very large, then we will get some kind of loss value here. For the in this case, actually, they are other way around. The L2 is in this side and L1 is on that side. Doesn't matter. So anyways, for the L1, which is this formula, for L1 we will get like, for example, in this case, if the error is -7, then it will be like about 8 here, or it will actually be -8, then it will be 8 here. So, but then for the squared error, we will get like 10 times higher loss value. So what it means is that the gradients, so the model will learn to go down to this part of 0 here in the middle, right? It will always point to that direction, right? So, but the learning rate doesn't change, right? The learning rate is the same. So what will happen is that the jump will be very large, like that, and here the jump will be very small. And basically, what it means that for the unclean datasets, for datasets where there are a lot of noise, where there is somebody entered the wrong values, the L1 works much better because it gives you the more stable kind of always the gradient. But for the datasets where everything is very clean, where you have very carefully entered your values, the L2 is better because you will get very fast convergence down to here, and then it will become smaller, 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 and it will go to very precise value. So, and the middle way, what we can use something in between both of those ideas, is that we could use the Huber loss or L1 smooth loss. There are all sorts of variations of that. So where you can have some hyperparameter, in this case the hyperparameter is delta, and you can use this delta to change the shape of your loss function to make it either more susceptible to noise or less susceptible to noise. So that's why, again, the loss function is a very important part of deep learning. And now we're going to implement another loss function. So maybe for the whole, I'm not sure, like, I think we should not give like complicated loss functions for home, but basically just you need to know that there are a lot of ways how to drive your loss gradients. So let's now go back and implement the Huber loss. So to the code, and the Huber loss looks like following. So we can write what will be it. So loss is, and by the way, there is one thing that you must know. Remember we had the variables class, right? Variables class where you have each of our data points or any variable as something that contains the value and gradient, right? In this case, these are called tensors. So the tensors are like variables. Tensors are like variables. And inside those tensors, we will always have prim data, which is a kind of like variable value, and we also will have prim grad, which is the gradient. Exactly one-to-one, the same thing as we did last time, but now this is calculated automatically. Before you had to calculate it yourself because we created so that you understand how it works. Now the same code is included in Torch, in Pytorch already. So you don't need to implement that because it's already implemented for you. So that part is ready. Then also we will not use anymore the numpy functions. Instead we will use the torch functions. So here we have the torch mean. So this is like average value of something. So torch mean of that part. So then we will use this hyperparameter, which is called delta, right? So self delta, and this should be squared, so we can square it, right? Like that. Then what we should do next is to multiply that by that square root stuff. Let me see. Okay, so we need a bracket here. So torch sqrt, again, not numpy sqrt, but torch sqrt, because all of the torch functions will automatically, not automatically, but will include basically the mathematical tracking of your gradients. So remember that we created like our own backward pass for any function. Here the mean, the average, or sqrt, or anything like that is also um, what is the name of that? Derivable. Basically, it's tractable, right? It's tractable. So you can get the partial derivative or derivative from any of these functions, and that's why we are using them from torch dot something, not from numpy. So here, let's say 1 plus, and then we have that part as well inside the brackets, and then there will be another brackets because we want to divide it. So self delta, like that. Self delta, this will be y minus y prime. Y prime, again, very interesting. If I would just flip y prime and y here, it will also work because the gradient will be automatic, like it will be calculated with the auto differentiation engine and would then just put a minus sign in front of the grad part. So here, let's add squared. So this should be squared. And then just the last part of our equation, which is -1, like that. So that's great. And then we need to return the loss here. Really hope that this part is okay. Now, so I will copy this equation implemented in the Google Classroom. Well, I mean in the Jamboard, sorry. In the Jamboard, basically, it will be really interesting that you can see that how the equation looks in the mathematical form and then in the code. So it's exactly the same thing, just in the code. So you can see that on the slide number 4. And okay, I see some problem in the chat. Recommendation, add this line. Oh. Yeah, thank you, Martins. There is something, I guess, regarding some environments where I guess the kind of some of the Intel-based libraries, which are at the backbone of the NumPy and Pytorch, might not work correctly. This KMP, that's an Intel library. So anyway, here, okay, let's ask question: is Huber loss was done? Plus, minus? Let me know in the chat if you have any problems. Thank you, Martins, for the advice for the Windows users. Okay, so this is the Huber loss then. Okay, I see. Oh, nice. Great. We have 5 pluses. That's excellent. You're working very good. Okay, so let's move on. So then the last part here missing, what is this? Anyway, so the last part missing here is to trying to make this to work as for the forward and backward pass, right? So this is again very similar to what we already know. So y prim equals to model forward pass, right, of the function going in the natural direction, right? So this will be then x and x classes which we will pass there. Again, remember that before we added the kind of like idea that with a variable around, like variable, like that, right? Remember we did this. But in this case, the data loader will automatically convert the x to the tensor type of object. And tensor, remember, is like variable before. So now we get out the tensor y prim and we pass in the tensor y, tensor x. So then here the loss is the loss function forward, again the same way as we did in the previous works. Why? We calculate how good is our model, the loss, right? And then we need to add the loss to our statistics. So the statistics will be here, losses, append, loss. And here comes a little bit tricky part. So this is the format of the tensor, but we want to have the kind of format of numpy or simple floating point. And in that case, what we can do is to try to convert it to the to something usable. So let's say the one way how to do this is by using data numpy like that. Now it will be usable as something that is floating point of numpy. Hopefully this line works, so we'll see that. Okay, that we can then append to this. So maybe we should write it as np loss. So this is numpy loss. So this is not tensor anymore. This is then a numpy value, right? np loss. And this will be just one scalar value. Remember that for all of our mini batch, we want just one number, one scalar value that says how good is our model, right? So we'll add that. And then for the backward pass, which happens only on training, because we are training it and then testing it and then comparing how good is the result for the test set and based on the training set, right? So then what we do here is we call loss backward. So here's a little change. The logic is exactly the same as before, only change here is following. We are not calling loss function backward, but we are calling directly backward to the tensor itself, because tensor already contains the pointer to previous function that was used. So what I mean by that is in the loss here, you actually have the fn, or what was there must be fn was something I forgot about, funk fn or something like this that I have inside. If you're starting debugging, you will see that in the tensors there are also pointer to previous function which you called, and that's why you don't need actually to call the backward on the function but just on the output of the function. And it works exactly the same way as we did last time using the numpy. So that is loss backward. And then the optimizer, of course, the optimizer then is the step. Again, exactly as we did with numpy. You already know how to do that. Then optimizer zero grad, again, exactly the same reason as in the numpy, because the gradients are accumulated. You can even run multiple mini batches and calculate the gradient of all of those batches and then run the optimization step, or you can do that every time when you have the new batch. So this is what we are doing. Okay, so let me check if this thing is working. I will add a breakpoint, and if it is working, I will drop it in the Jamboard, and then we should be done by working with very simple regression model using the Pytorch. Okay, so we see that this is a numpy array of float, so this is not optimal. Maybe we should select the first variable here like that. It could work also with the previous line, but this will be more clear. Okay, man, it's not like that. Non-dimensional 0. Okay, it should be like that. Let's see. Let's run it. See if it works. Yeah, it seems working. We'll see how the loss plot looks like. After 10 epochs, we will get the nice plot here. Yes, you see the loss plot is working. So the train and test loss is reducing about the same space. So it kind of points that the data set is quite uniform, because it seems like that they both kind of learn about the same thing. So that's one. Yeah, it's just like, it might also mean that there is problems with data or with model, but it seems that it's working down. So yeah. Okay, so this is the only part necessary yet for the running of the model. So I will drop this also to the Jamboard. As you see, we are only adding few lines and everything starts to work, right? Because this is already all of the theoretical part we covered. Now we're trying to make it work using the very powerful Pytorch library, which does the auto derivation, the partial derivatives for you. So here, let me ask then the question, is training working plus minus? So, and then we will jump into the next part of today, which is those categorical parts of the inputs. Here I see some interesting results in the chat. So int has no attribute of that data. So how that could happen? Loss data int loss function. So you call loss function forward. Then if you get something with regards to int, okay, got it. So Martin's works. Okay, so then for Muhammad, so there is raise attribute error has no attribute format model has no. You have a typo there. Layers. There should be layers. See, in the model side, if you go in the model, then you call self layers. So this line variable name should match this line variable name for the Muhammad. Okay, and for others, I will wait for the others. I also dropped the code for that part to the slide number 5. So please let me know in the chat. Let's wait for others also so that it would work for you. So it's training, and then we will move on. See, okay, what else? Can we reduce count of epochs? Right, definitely you can. No worries. It's just right now as it is. We will add more stuff there. Maybe it will be good that we have that amount of epochs. Now I assume we have about three people ready, but before we had about six people ready. So let's wait for others also to catch up. So here is the code what we needs to be finished. Still those same three people. What's up? Can I help you somehow? Please copy also your errors as you saw before. I immediately can help you showing where is the problem. Yeah. Thank you for the update at least. I don't have the necessary library, so just to help you out a little bit on that front. So what you need to do is then to click on this bottom part terminal, right? And here you can just install using probably the pip3 install, and then you just type the name of the library which is missing and hit enter, and it should install those libraries. Also, you can look up exactly the command for installing the Pytorch from pytorch.org. But basically, it's really simple to install libraries. It's just pip3 install and then the library name. So, okay, we have some other error. Thank you. So the 70 line 79, I hope that the line is similar to mine. 79 here. Okay, sorry, the layers. So there is a tab. There was a tab. Yeah, unexpected intent. Oh, so that's so funny. While I was talking, I accidentally pressed tab here, but it should not be tab here. So of course, remember the tabs. We talked about that in the very beginning a lot. So the Python have the scope. So the C++, you have the curly brackets. Remember in C++ you have these kind of brackets, right? So this in C++ means this is the scope, right? In Pytorch, the scope means the tab key. So this is the kind of like, this is the scope. And yeah, so you should not, for the error is here because the tab is not in the same way. You have the error means indentation error, which means that your tabs are not okay. So you should have the tabs correctly. So here is the tab. All of this is in the same tab level. Then all of this is in the same tab level. Then inside here, all of this is in the same tab level. As soon as you will get the wrong tabs, nothing will work. So please check your tabs. I will wait for maybe more people ready. So 1, 2, 3, 4. Yeah, I think 3, 4. Yeah, we have about only 3, 4, or maybe 5. Anyway, so we are almost ready. I hope that VPN also can get this going. So anyway, this is on the Google Classroom already. I mean on the Jamboard. Sorry again, on the Jamboard we added. It should be there. Should be fine. So now let's look at the next part. So the next part will be why it's not working? Okay, the next part will be the implementation of the X classes. Remember the categorical values, like is the car automatic, manual, is it sold by the dealer or a simple person, what brand is the car, and so on. So those will be X classes. So let me show you. So the X classes, so those are the kind of like brand, the fuel type, right? Fuel type, the transmission, is it automatic or manual, and so on, right? So those are the X classes. There was one more. What was is it a dealer or individual, and so on. So these are the X classes, okay? And for these types right now, we just say that, for example, the fuel type is like 0, 1, 2, 3. So there is like 0 means this is a gasoline. Then 1 means this is a diesel. And 2 means it's a LPG. And 3 means it's some kind of other gas, natural gas. They don't have electric cars there. Anyway, so these will be the fuel types, right? And this is what's we getting 0, 1, 2, 3, and so on, right? So everything seems fine, except we have a problems. For example, so let me see. So if we have, it could be looked at many ways, but one way how to look at it is using the sigmoid, for example. So if we have the sigmoid, so this will be the x and y axis, okay? And then remember we have a sigmoid. This is nonlinearity function, right? It goes something like that, right? And then we have those data points, right? So let me see. So if I have the data points so this will be gasoline, then there will be the diesel, then there will be the LPG, natural gas, and so on, right? So, but then there is a kind of strange problem, because if we have that kind of like distribution of the our inputs, so the non-linearity layer's idea is that we want to reduce the effect of some value. So I want to be able to say that the gasoline is not important in the price when the car is younger than, let's say, 2020 or something. Okay, what's again, there is some message. If computer working is slow, does it affect the result of the graph? No, the effect of the loss function should not be depending on your computer speed. It just will be slower, so no worries about that. Anyway, so I'm trying to explain. So here we have this kind of data representation, and we plot it here, and there is the sigmoid, for example. So what we get is very strange effect, so that the gasoline car is somehow better positioned than LPG or natural gas car, right? Because if I want to say for this model to learn, please learn that natural gas is not important in this model. I will need to go much longer distance to get here, and the model will need to work a lot harder to understand that these data points are not actually something that is like a scalar value, like production year or something, but they are all the same. So I mean, none of these data points are specifically more important just because they have these indexes. Because of course there's nothing telling me that I can give the same indexes in different order, right? I can say that, let's say then the gasoline will be 3, then let's say this will be 0, this will be 1, this will be 2, whatever. And then now, again, we have a new disadvantages. So then the gasoline now will need to learn so much more longer to get to this side of the sigmoid than the diesel, for example. So it doesn't make sense. It's totally nonsense to try to encode categorical data types as a scalar numbers, because they are not kind of like, if this would be a production year, right? Then this is logical, so that the later this the production year, the more should be there's some kind of correlation between the nonlinearity. So I mean that basically the older years will go here, then we can bias them and move them around in a specific way. But if this is a categorical type, it's a nonsense to try to code them as like indexes. So what would be a better way to code them is using something that is called one-hot encoding. So the one-hot encoding looks in different ways. So let me write, so for this part, let's say never use this. So for classes, categories, never use indexes. But what we could use instead then is something like, for classes and categories, could use one hot encoded representation. So how they look like is following. So instead of defining that the fuel types will be like 0, 1, 2, and so on, if we have 4 types of inputs, then what it means that we need to have vectors of equal sizing. So this will be then, let's say 1, 0, 0. So, and then the next one will be 0, 1, 0, 0. Then the next one will be 0, 0, 1, 0, and next one will be 0, 0, 0, 1, right? And now all of these are positioned in the space in the same position, because basically, if we imagine that this would be 4-dimensional space and these will be vectors, then all of those vectors will be the same length, right? If we calculate the length of this vector, this will be length of 1. This vector will also be length of 1, length of 1, length of 1. They are all at the length of 1 from 0. So they are all of these nice vectors, they all are, let me make a color here. So all of these guys are in the same position, 1 here. So their vector is at the length of 1 from 0 at the same position. So it means that gasoline or diesel or anything else is not more prioritized than other, okay? So here, let's say if we then define it as this is gasoline, 1, 0, 0, vector, right? The other vector value of diesel is here, like that. And then the next vector value is like that. And then again, the next vector value is like that. So you see that now we get a representation which is much more stable and much more like better than before, because if we just now switch around like gasoline with diesel or LPG in different order, it doesn't change at all the property how they plot on the non-linearity, or in what is their distance, because here the distance from 0 to any of the classes are directly tied to their indexes, right? So and here they are independent. So my question in the chat is the um, is the one hot encoding clear? Coding clear. Plus, minus. If minus, please try to add some comment what is not clear about one hot encoding. Why the class data sets, I mean the categories of the classes would be necessary to encode as that. Okay, I'll wait for you to a little bit to digest this information, and then wait for your response on the chat. So I assume that this is not clear, right? Or is it clear? Plus or minus? Please let me know in the chat. Hello. So should I assume that this is not clear? So maybe I should somehow try to plot this again. So if we look at this situation from top down, right? So let me see. So what we want is our data inputs which are not related to, which data inputs which are not related to, so to some specific scalar value. So I mean the production year, right? When the car is made. This is a scalar value. This is some kind of integer value which has a meaning when it increases, right? But for the classes, like this is a gasoline, diesel, or LPG, it doesn't have any sense of the value increasing. They are all the same categories, right? So they are all the equally important in very beginning, right? So let me see. So if we try to present this wrong way, so let's present again the wrong way with the blue, and with the orange we'll present the correct way. So this is from top down. So again we will see that they will be located something, well, somewhere along these lines. There are 4 points, right? 4 points. And then let's put those one hot encoded representation. So they will be actually something like this. So these are one hot representations. So there will be, so this is the gasoline, diesel, natural gas, LPG. And then here these blue ones are the same with index representations. So now the question becomes, if they are all the equal importance in very beginning, because we don't want to say automatically just because the first class is gasoline, it is much more important than other classes, right? It's like nonsense, right? So then what is the distance between those points? So here from zero distance to this point, to this point, to this point, all of those distances are equal, right? So this is equal, this is equal. But then from the blue points, this is absolutely not the case. So unfortunately, this guy which got the last index got like 4 times, like 3 times larger distance than this guy, for example. So it's kind of, you want to make that the all inputs are equal when they are not related to some scalar value, because otherwise I can just change the order of these and it will give me completely different results, even though they are not, the order is not important. The order is totally irrelevant, but the way how we encoded the data is very important. We need to make sure that they are all equal, and the one way how to make sure that they are all equal is using this kind of vector representation of one hot encoded vectors. So here there are 4 dimensions, but in this plot where I give you, this is reduced just on 2 dimensions. So I mean, if you had just only gasoline and diesel, you could plot it on 2D as well. So is it clear now or not really clear? So let me know again. So is it clear now, plus, minus? Should I keep trying to explain? It would really help if you just give me some question, so in some direction which is not clear, then I can help you understand. So this is regarding the data inputs. We cannot like put them as an indexes inside our model. It doesn't work like that. And I'm trying to explain why it doesn't work. Okay, I see 1 plus. That's encouraging. Thank you. Let's see what about others. Excellent. I see 2 pluses. So 3 pluses. Excellent. So the idea is that we want to represent our input data as something which is equally important, not something which is arbitrarily set just by our indexes or our choice of order, right? Which is like nonsense. So then in the 7th slide, the only missing piece now is following. So one hot encoded representation is good, and we should use that in many cases. But there is an even better way how to do this. So even better way how to do this is to use, instead of one hot encoding, use learnable encoding, which means exactly the same thing. Nothing changes here, only that we create that these vectors are actually learnable. So what it means that there is weights inside. So there is, let's say, weight 1, weight 2, weight 3, weight 4. By default, all of those will be zeros, and it will make that all of the, or random, by default, all of those be actually random. So they will be random. It means that all of the inputs will be equally important. So here will be W5, W6, W7, W8. So these will be learnable. So I mean, what is learnable is that we will calculate the derivative for those weights in our function graph, and at the end it will slowly change so that the position that it will learn that the gasoline is important in that direction, the diesel is important in another direction, and so on. So basically what it means that it will make that, for example, LPG and natural gas are more similar than the gasoline and diesel, for example. That will happen eventually. So here, this will be also changed to this. This will be changed to this, to learnable parameters. So they will be random in the very beginning, all of those values, okay? And then slowly they will learn what is the correct values for what is the correct vectors for these guys to make them usable in our model in a more efficient way. So initially W's are random. So in the end, the property here is that, let me show you how it at the end might look like. So after the training, so initially before the training we have the same situation. They will all be approximately at the same distance because they are all random. They will not be so nice as one hot encoded vectors, but still they will be approximately same distance because they are random. And then after the training, so let me write with the green one, after the training they will learn that, for example, the LPG and natural gas is more similar, and then the diesel and the gasoline are more different. So after the learning, this might happen, that the green positions would be in those vectors. And they are just the encodings for the inputs, by the way. Like, you can imagine them as like the first layer of your model. So are learnable encodings clear? So but let me know, is this clear now? Plus, minus. If minus, then try to write what exactly is not clear, and I can try to explain. Again, the process of how it's learned, this is exactly the same as in the linear layer. Actually, this is a linear layer just without the bias, you know? I see 1 plus. What about others? Okay, so we'll try to show you also one more thing. So we will construct like a learnable matrices. So this will be kind of our learnable embeddings, and then we will select by index. So there will be index 0, 1, 2, 3, 4, right? 0, I mean 0, 1, 2, 3. And we will select from that matrix, so that if we are talking now about gasoline, that we will select this row, right? If we are talking about diesel, we will select this row and then pass it to the model. If we're talking about LPG, we will select that row. If we're talking about natural gas, we will select that row. And we will send that to the model, and the model will slowly send back the error gradients, which will change the values of those weights. And at the end, we will get really nice kind of representation. So that's why this part is important. And again, just to remind you, the initial idea, just passing the indexes to model, very wrong idea, very bad idea, because like you can just swap them around and you will get totally different results, which is not what we want at all. So the one hot encoded better idea, it's actually sometimes even very good idea. And then the weighted learnable, like kind of vectors, is even better idea. So okay, let's then put this in the code. So this is the last part necessary to submit the task 5.2. So here, let's go. We have X classes missing here, right? X classes is missing, but we want to add X classes ourselves to use them. So here, we will then use the self embeddings. I will call them M's, embeddings, torch, and module. The thing is that we have, I think, 4 embeddings, 4 types of categorical input data, right? 4 types of classes that are our inputs, actually. So 4, 4, 4, 4. Let me see, I in range. So these will be the elements. So here 4 elements, and those 4 elements are following. Or maybe we could just write it as a data set full labels. Or let's write it more simple. For label in data set full labels. So inside those labels is what you already know: the brand, the fuel, the transmission, the dealership, right? And each of those contains a lot of classes, right? So then we have self em's append. We will append something which is called torch and embedding, which is basically just a very simple matrix. This is nothing magical there. This is just like a very simple two-dimensional matrix, exactly what I showed you right now on the Jamboard. And in that matrix, what I want to say is that I want to have num embeddings, which is the same number of rows, which are the same as the labels, right? We could actually write it as labels, because there are many labels, right? And then the other dimension which is necessary is how many dimensions we want to use for the columns, because now there is something interesting happening. Nothing tells you that we need to use the same amount of dimensions as in one hot encoded vectors. We can change it. We can change it to any number of dimensions as we want. It's not necessary that the column count matches the row count, right? If you look at the last slide that I gave you on the Jamboard, it says that it means that you can easily imagine that we will have only 3-dimensional vectors, not 4-dimensional, and it will work the same way. So that's a really fascinating, cool feature. So let's try to reduce the number of embeddings actually to 2-dimensional. So embeddings will be 2-dimensional, even though the inputs might be 4-dimensional, like the fuel types. we can reduce them to 2 dimensions just because we will have 4 rows of the matrix, but 2 columns of the matrix, and we will have exactly the same properties as the learnable embeddings, or like I showed you on the slides. So that's cool. Then here in the inputs, we also need to add those things. So plus, we will have 2 dimensions times 2 dimensions times len of these guys, self dataset full labels. So that means that how many labels, or these like 4 types, brand, fuel, transmission, dealership, you could even write here like manually number 4. It's the same thing. So basically 4 labels and then 2-dimensional embeddings for each of those labels. So that part is here. Then the last thing necessary is to add all of those embeddings. So here we will construct this part. So there will be the list of X embeddings. And this list will be following. So for I embedding in enumerate, so we will add the indexes of each of the layers, or not the layers. This is again really nice way to show you that in the Pytorch you can have parallel paths of your functions. You don't need to do everything in sequential, like in Torch, Keras, or whatever. You have these sequential stuff. So here you can have, like in parallel, many types of function directions which you combine later. So here in parallel we will do these embeddings. This is not sequential type of model. So here append X classes. We want the same embeddings for same inputs for all of the batch samples. So I mean, like we ignore batch. We want that the output will be batch, comma 2, not the. So basically that's why I'm using the colon here. I. So this will convert. So this line will convert the. Oh, sorry, I forgot about embedding actually. So embedding. We could actually split it in 2 parts. It will be much simpler. So here we'll have X embedding each, which is then embedding forward pass. Again, the same way as in any other functions. X classes, the batch I, and then we will append this to this guy. Okay, cool. And what's happening here is that we are converting something which is batch, comma 1. The index of a class, right? The fuel, the diesel, gasoline, whatever, to something which is learnable, batch, comma 2, with the same length between them. So this is much better representation. So that's fine. Then we will concatenate them together. X embedding torch cat. So this means putting all of those vectors as a one vector. X list embeddings. List X embeddings by dimension of -1, which means please put together all of my 2-dimensional vectors in just in one large vector, which in this case will create the 8-dimensional vector. And then the last thing is I also want to put the X cat, which is also want to put together scalar values, because we had like production year and all sorts of those scalar values. I want to add them as well. X embedding dimension -1. So please put together the scalar values like production year and other things to my embeddings. And then the last line is exactly as it was before. I actually should not delete it. So self for layers forward xcat. So I'm now passing to the model all of these combined vectors and getting the same output. So only reason why this works is because up here we have this in features changed. If we didn't change the in features, nothing will work. because the model will have wrong matrix dimensions. You cannot do the dot product with wrong matrix dimensions. So that's why we added that part. Oh, sorry, in the front here, this line is not necessary. So I will check if this works, and if it works, I will drop this in the Jamboard and let you catch up. Yeah, it seems to be working. Now we have much more interesting information in our dataset to work with. I mean, in our model. So the model now eats also the categorical data, not just those 3 data points. So now I'm adding this to the Jamboard, slide number 8. So I'm adding that to the Jamboard, slide number 8. And we will wait for everybody to catch up a little bit. So now the plot is working. Okay, so and you can then submit actually the task. So is 5.2 task ready? Plus minus. If you have some problems, let me know. If something is not clear, let me know. And I will wait for you to submit the task. And then we will do the next task. So I will also open the next task. Next task will be 5.3, which is implement R2 score. And I will explain. So the idea is that we have our data set, right? And remember, your homework was to implement, I mean, we have our model, but in homework we had to implement normalized root mean square error. And the idea is very simple, because actually in the plot you see, I have also the bottom plot there. And the idea is that I want to have some kind of value to measure the how good is our model in some understandable way. So the best way would be if I get 0, then it means the model is bad. And if I get 1, the model is good. But if I get the loss value of some kind of if I get loss value of 0, that means good. But basically, if I got loss value of 112 or something, it doesn't tells me a lot. I don't know if it's a good or bad model, right? So instead, we're using some kind of parallel metrics, and this is also a very good idea to use parallel metrics for evaluation, which are not also the same metrics which you use for the training. Okay, I see somebody has an error. Thank you for sharing that. We can try to help you. So the error is 16,3 and 11,3. Shapes cannot be multiplied. So 16,3, 3, 3, 3, where we have 3, this is an output. So most likely you did not implement this line correctly, or you did not implement here the xcat. So the forward is xcat is the concatenated version of those 2 inputs. Again, you cannot do the dot products matrix multiplications with wrong shapes. So that you should understand. So I hope you can check those 2 lines and make it work. So then in the slide number 9, I will drop you now here the formula. I will try to help to start working with it, but I want you to submit this work yourself during the class today, because we will also need to talk today about the classification, and we cannot like sit around here for 1 hour and do nothing. So you need to do this yourself quite reasonably fast. So here, this is the metric R2 score. So this metric will give you the result of, so it will give you the, let me think how it will work. Should be something around those lines that one means one means excellent, 0 means very bad. So this is really nice metric, basically. And sometimes you can calculate it also in the negative direction, and then it would be like completely opposite of very good, you know. So, but now it's very simple. So what we have here is the y. This is the ground truth. This is the predicted value, right? Then this is the ground truth, and this is the average value of the ground truth samples of that batch. And then you calculate using this formula. Very simple way, but very useful way. So let me show you how to start with this equation, and then you will finish it and submit in the Google Classroom as a task now. So let me see here. We already have the R2 plots here, but we don't have here the R2s. So let's add that one. R2s. So this will be the holder of those R2s. Then we also need to add it here. I forgot to add those two lines. So here R2 train append MP mean of mean value of these R2s, which we will calculate. Oh, sorry, dropped it in. So mean value of those guys. Also mean value here for the test set, like that. Then here, I will help you out with very beginning. So let's see, R2's append R2. So this is something that you need to calculate. R2 here, this is to do for you, right? And to get the variables for you to make this work, I will help you out. So MPY, we can convert this to the data numpy. So now you will have numpy variable here, and also this thing npy prim. We can convert to y prim like that. Let me check that this is working. We'll drop in the breakpoint. And basically, this is what you need to do. You need to write one line of code to implement that very small equation, and you will get 500 points for this course. So, and you should do this now, because after you do this now, we will move to the next task. And I want to see who is the best in the course now, who is capable of doing this very, very simple task now. So I will drop this also to the Jamboard below the that equation here. Now it's adding. Now it's added. So here is that part. Now let's see who will be the first to submit the task. So the task 5.3, who will be first who submits that task? Who will get the cookie and who will be the best of the course for now. Meanwhile, at some points, maybe I will have time to check what is your current status of your Google Classroom homeworks. At least so you should submit the homeworks quite quickly because next week is last time for this mini course, and we will put the grades and marks for you if basically very soon. You can pass the course if you submit all of the live session homeworks with minimal mark, but if you want to get some better mark, you should then also complete the other works, like the homeworks basically. Okay, I see very strange error in the YouTube live chat. Line 32, the syntax error. What it could be. There might be possibility that you're running it with totally wrong Python, like maybe Python 2.7 or something, or something which is not like like the latest Python versions. Maybe you should check that, but this is not actually the coding kind of problem. It seems like most likely there is like the wrong Python version or something. Yeah, then if your operating system doesn't support Python, then you can use the Google Colab. There is absolutely no problem of finishing this course with any kind of computer. So you just open the Google Colab, which is the online way how to run exactly the same thing that we're running right now, and I will show you just in one click how you can run it. And you actually can access also the GPUs here on the Google Colab in the online here. And next time we will work with the more advanced visual image recognition tasks. Then we will actually use the GPUs. So here, if I just open Google Colab, it's called. Let me write you what it is. So it's called Google Colab. So this is a way how to write Python inside of your browser and then run it. So here I just drop the same code, copy paste. I do nothing, basically just drop, copy, paste. Then I press run here. Everything should work. So no problems with libraries, with strange Windows Python errors or whatever. So yeah, it's basically running. It's maybe not super fast, but it's running. If you run it on GPU, then it's super fast. Okay, maybe it's downloading actually the files, but it should work. So yeah, definitely use Google Colab if you have some problems. So I see that now it's seeing the execution below. Everything is nicely working. So see, it works. It gives you the plots. Everything works directly in your browser with 2 clicks. So there is no excuse of not being able to do the homeworks or the any of the classworks. So it's working in Google Colab without any problems, even if you don't have a powerful computer. So use Google Colab if nothing is something not working. I will also check what is the progress of who is the best in the course now for being able to finish this small task. Oh, we have somebody implemented the task, and that's excellent. So Guntis have submitted the task. We'll check what he submitted. Okay, he submitted only that line, but that's fine. That's totally fine. Just submit that line. I was expecting the whole code, but that line is also fine. So let me check it. I will copy it on my side to look at it. I think it seems fine. At least I don't see like a major problem with it. Let me see. So I will try to run it. Okay, what's happening? Except he is using a bit wrong variable names. This is strange. So not like that's why I was wanting you to submit the whole code, because if you submit something like this, even the formula looks fine. I don't know. I cannot verify that your code is working at all. So I mean, right now the your formula doesn't match the code, and I cannot run it properly actually, because you cannot execute the MP sum to your torch variables, like the y and the y prim is torch variable. You cannot just call MP sum on torch variable. I specifically explained you and give you the template how to do that. So I think like I cannot like give like total 100% for this work, but at least it's a good attempt. So I cannot verify that Gunt is done this properly. Okay, there's something strange about it. Okay, sorry. I guess I did some mistake. So the way how this is formulated, I guess it's giving me the values a little bit in the wrong way. So so on the Jamboard I should fix it. So the 0 is okay. Let me think. Okay, correlation R2. Okay, the way it's formulated, something is strange. So let me see. So no, something is strange. It should be 1. If the 1 is if the mistake is 0, yeah, it should be that 1 is good. Yeah, this is correct. 1 is good. There is something strange. Anyways, we'll wait for the results. Okay, it seems like that the formula is even wrong, I guess. I mean, not my formula, but Gunther's formula. So the output is wrong actually. So let me see. See. Yeah. So now it's a lot better. Yeah, and this can be okay. Cool. Yeah, definitely. So Gunther's formula unfortunately is wrong. So the formula on the Google Classroom is correct. I mean on the Jamboard, but what he submitted is not correct. So not correct even in the variable names, but also not correct in the principal. So we'll need to wait for somebody who can do a better job. But it's thank you for attempt at least. So that's a good attempt at least. So yeah, let me see. Yeah, the only thing is that the variables or the minus there. Yeah, so it actually can go also in negative. So 0 is very bad, and minus infinity is like completely opposite to good. So basically, so this is either inverse to good. So okay, so this will be very bad. This is bad basically. So no correlation basically. Here is no correlation. So these are the outputs, but the formula is the same. So first thing when I got the result from Gunt is then I thought that the formula is something not okay, but actually his work there is something not okay. So anyway, let's wait for some other responses, and then we will move on to the classification part of today, which is also a very important part of the deep learning. Ciao. Nezinu, ko tas nozīmē? So I see another input. So the other one who submitted the work, classwork today, Elena. Let's see what is her result. So the formula here is, let's see. Yeah, so this formula seems, let me see. Haha. Unfortunately, not super precisely correct. So just to try to explain that this symbol means average value. Of course, in mathematics, it could mean some other things as well. But basically, this means average value of y's. The best case, this is average value of all y's in your data set, but it could be also average value just of your batch. So please create that this y is an average value of your inputs, okay? I mean your outputs, the ground truth. So the thing that was submitted by Elena is not totally correct, but it's better than Gunte's submission. So let's wait for somebody else as well. Okay, thank you. I will make Mike's mic more louder. But Eline's work was not totally correct, but it's better than Guntis. So I'm still waiting for somebody to submit correct answer to this task. Okay, so I'll wait a few other minutes and then I will show also some answers. Okay, so let me then show you how to do this properly. Okay, so actually I see another task. So the Martins have submitted. Let's see if Martins have the correct answer. By the way, Elena's answer was not so incorrect. There's just one small mistake there. Oh man, seriously. Okay, not sure exactly why are you doing that, but the answer also to the Martins is not correct, and it seems very similar uh, to the answer of Elena, which seems like that might be copied from Elena, but I hope that it's not true because some other parts is very different in that code. Anyway, so no cookie for but today, but like at least 3 people have done a good job of trying to do this. So let me show you how to do the. So Elina, Guntis, and Martins was the ones who attempted. Unfortunately, not totally correct. So just a second, we'll try to show you. Okay, I had the telephone call. That's why it was a little bit stopped. So anyway, here we have the formula. Then the top part of the. So I think the Martins had the following mistake, except that there is a lot of other things which didn't work. So is that there should be brackets around here, of course. So then there will be 2 brackets here inside like that, and then in the top part we will have MP sum of the y mpy mpy minus mpy prime squared, right? So this part, and then in the bottom part mp sum, and here will be the mp y minus so let's add this one as a bracket as well. So maybe I liked actually that Elena split this equation in multiple parts, then it may be more readable. So, but here the idea is that we will calculate MP mean, the average value. So this is not a loss function. I don't know why both of you added here a loss function, which is I cannot understand, because loss function is the Huber loss, and this is nothing related to this. So here either we have the MP of y, or we could also calculate here the MP of your dataset, whole dataset. That would be even better. So the better way would be to calculate not NPY, but to calculate NPY of dataset full, or what was it? So dataset full dot y. So if you would calculate average value of whole dataset wise, that would be even better. But of course, that would be good if you calculate that once and then use just only that variable there. So you don't need to run it every time. So if I run it, you will see that immediately we'll get like very large negative values. It means that the output is not correlated to, like it's inversely correlated to the input. So very bad output. And then it slowly becomes slower, like closer to the zero. It comes closer to the zero, but it takes very long time to get in the positive direction. So the plots look like this. It seems like that it's going from minus to zero, but this is not the case. It goes from minus to the 1 actually. So, and the one way how to make this a little bit more visible, so the last stretch of the difference is that maybe we could add some kind of max part. So here, so this will be then, or maybe we could call it like max of of R2, and let's add some kind of, let's say, -1. So I mean, making that it will stay flat in the plot in the very beginning, and then when it starts getting closer to actual usable range, which is from somewhere between 0 and 1, then you will see actually the plot becoming better, and hopefully that will be some meaningful information in the plot as well. But this part of equation, of course, is just for visualization. So you see that now after the fourth epoch, it starts to grow the R2 value, and the R2 value is, you see, is much more kind of informative than the loss, because loss already seems to be converged, even though R2 value you see is not yet converged, and also the R2 value is not great at all. It's really in a minus. So if it's in the minus, it's definitely not a good model right now. Probably if you add more parameters and make the model more, so you could add more parameters, you can make a better optimizer. So let's do that as well. So R2 score, I'll drop the code of the R2 score also to the slide number 10. Again, really thank you for those 3 people who actually tried to submit this task. You see that you were not far away from the correct answer. It was very close to you. There's just a few small issues there. So, okay, so that part. Then what some things that you can do to make better R2 values. So first, you can change the optimizer to Adam, for example. So the optimizers, remember we had the stochastic gradient descent, SGD. So if you change it to the Adam or RMS prop or something like that, so those optimizers, if you look at, for example, in the Google or Wikipedia, you will find that these algorithms of the optimizers have really interesting properties. So if you know the gradient, like the direction of the error, right, and you know this in between batches, in between epochs, you can estimate how fast this gradient changes, and you can learn also like kind of what is the speed of gradient change, like the second order derivatives, and then if you have the second order derivatives, you can basically you could theoretically converge like much faster. You don't need learning rate basically at that point. But anyways, these optimizers are much smarter. They have momentum inside them. Actually, if you go in Adam, you will see that you have the betas, epsilons. They are kind of parameters which controls the momentum, and it makes your optimizer much more faster to converge. That's one. The other thing what we can do is to add more parameters. If you add more parameters, you will have much more powerful model. So for example, we could add, let's say, 30, so this will be like a lot more parameters, 16, then from 16 to 16, and then from, let's say, from, or maybe to 8, and then from 8. So that we can try out. Hopefully we could get a little bit better results by adding more parameters to learn. So there are more information which is encoded inside weights, and there is a stronger also the stronger optimizer. Okay, and we will see what is the result of that kind of model. We will immediately already see really good results. So you see that R2 is over minus, so R2 is closing into 1. So R2 is already 0.5. So you see it's so much more better, right? So the only thing what it changed to do is to add better optimizer and to add more parameters to the model. I didn't change anything else. So, and you immediately see that your result of the actual usable model is now about, like, you can imagine like 60% accuracy or something like that. But it's actually like R2 score at 0.6. You see that it's at 0.6 right now already. So really powerful ways how you can improve your models just by changing very few variables, right? They actually called hyperparameters. So these things that we change. So I dropped these things into Jamboard, and now I will open the last task of today. That will be also the kind of very important part that we need to finish before the homework, so you would be able to do the homework. So the task will be the 5.4, which is the classification task. 5.4 classification task. Now I'm opening it. Please download the template for 5.4 task. Again, those of you who have the Windows with all sorts of strange problems of downloading text files, then I don't know, like, just try to download it somehow. I mean, I could help you out by just so making the end of the file as txt. So just because Windows do not like Python text files, which is like ridiculous. So .txt. I will give you a link also here in the chat if somebody has the problems downloading that file. So 5.4 template. Just a second. Trying to give you the template file. So, okay, I uploaded the same file to my server using txt at the end. So I really hope that if you pick the link from the chat now, that link would work on the Windows. So yeah, you can try to do that. I will add also this to the task in the classroom. So for Windows download problems, could use the txt at the end and then rename to Py. That's really strange stuff. Anyway, so please let me know that 5.4 template is ready. So is 5. Or you could use not Windows, basically Linux and any other operating system basically would handle this. 5.4 is 5.4 template, okay? Ready? Is 5.4. So the 5.4 template ready to work. So it's actually called 5.3 in the file, but it doesn't matter. So so please let me know, are you ready to work for this last bit of today? Because otherwise, if we don't go over it, it will be very hard for the homework. So I will open the code in myself as well. So this is again the template. It's a little bit changed template from the one that you saw before. So it's very few changes. So, and I will explain what is the. I'm back. So see your URL. Thanks. That's great. So I'm happy that I introduced some of the people, or hope maybe you already know that in Windows you can do things from command line as well. So anyway, see URL works. So that's great. Thank you, Martins. Anyway, I will explain the changes. So this will be not a regression task, but this will be classification task. We will try to classify from the inputs, like, for example, car price and the car production year and all sorts of other embeddings. So from those, we will try to predict, is this a car of a diesel, petrol, LPG, or natural gas? So we will try to predict which type of car is it, right? So this is our task. So that's why this has changed the data set. So now the X contains also the X will also contain the card price. So where is the X? Somewhere is the X. Yeah, so here there's X. And the Y prob, or the Y probabilities, or the Y hot encoded will just predict one of these four classes. So that's the task. So that's the change. Is there anything else changed? So we will need to also change this model a little bit, and then we'll need to implement new loss function, and we will have a new metrics called accuracy, F1, and so on. That's really nice, okay? So for the classification task, it's easier because you can calculate what is the accuracy of predicting some kind of class, and it's kind of similar like R2 score, but it's more like intuitive. So here, let's do the first thing first. So we have these four classes, right? And we should convert them into one hot encoded representation, because one hot encoded representation also, what it means is actually the it means the basically it means the also probability distribution. Remember that it could mean the same vector length between classes. It could also mean that one class is 100%, then another class is 100%, and so on. And to do that, it's actually very easy. So here, let's use a function. So there is a inside torch nn functional, which I only asked here as a function f. This is common way how you write torch nn functional. And here inside that we have the one hot. What was the name of that? I think it was one hot. Yeah, one hot. So there is a function called one hot, and in that function, if I just drop in directly these indexes, it will produce me nice one hot encoded vectors like 1, 0, 0, 0, 0, 1, 0, 0, and so on, right? So depending on the sample, it will create me the one hot encoded vectors, which we will actually interpret as 100% accuracy for this, 100% accuracy for this, and this is something what we want to predict. Remember, in previous task, we had inputs which had the kind of distributions of classes, right? The categorical inputs. In this case, we have output of the prediction of the which class is it. So is this a diesel car or is this a gasoline car, okay? So I'm dropping this line of the code also to the Jamboard, slide 11. So this will be one hot encoded representation. I will write down that we will do the classification task. So the task is to predict the probabilities of the classes depending on the inputs on types of the cars, right? And the prediction task is to predict which type of fuel does the class have, right? Does the car have? So that's the definition of the task. Now let's see. So the way how then to present this is following. So if we imagine the last linear layer, okay, the last linear layer should now contain something like this. So the last linear layer is these two things, so the weights and biases, right? And now it creates this vector. This vector should be the same dimensions as the classes what we want to predict, the similar idea as for the inputs, right, for the embedding layer, but this is just for the outputs. So the logits should be, logit shape should be then batch comma output classes. So this is the shape what the logits layer should be. So the not layer, but the output of the last linear layer. Output of the last linear layer often in the classification is called logits. So that's one. Then we also have the probabilities, which is also the same shape. See the probabilities, right? Prob. But there is in between those two things, we have specific function, which is called softmax, which is kind of similar to a normmax, hardmax, argmax. Basically, they are trying to make that the probabilities of the last layer is actually something which we could use in probability theory or information theory, where we have kind of like sum of the probability distribution as one as a 1. So the sum is 100%. That's one property. Another property is that the output of the softmax layer, which softmax function, actually the output is very similar to the hard max function. So you can imagine very easily, you can imagine that we can get the probability output of sum of 1. So this vector is sum of 1. So is this a diesel car, is this a petrol car, LPG car, or some other car, right? We could easily do this just by adding here the output and then dividing by sum without the exponents. So without the exponents, it would also work fine. There will be no problems, but it will be not as similar as the hard max function, which means that hard max or argmax is that we want to make sure that the outputs are as much as similar to the distribution where everything is 0 and 1 is 1. So this is what we want to have, and if we would just not have these exponents here, just the simple summation divided, then in that case this difference between values would be less visible, and it will not modulate the kind of probability distribution as we would like to have with one hot encoded vectors. So this is a new function called softmax, very simple function. The derivative is a little bit complicated, but this will give you the output of the probabilities where the sum of that vector is 1. And this is then usable for predicting the, like which car is which and at which probability, right? So that is one part. And then the last missing part is that we also need loss function, right? And for the loss function, we will use something which is called categorical cross entropy, which comes from the information theory. Actually, it was designed when, like with the entropy, the KL divergence, and all sorts of those things, where the idea was that to measure what is the loss of data over binary transmission. That's why it's in information theory. When you try to like it was, I think, in the 50s or some time of that, when they had the digital transmissions over air or over the wires, then you want to have some kind of calculation how much of information is lost, and then you can use the all sorts of entropy type of functions, and this is called then categorical cross entropy. Again, I think I gave you on the link also a derivative of that. Usually with students we do that in NumPy, but since we don't have time in this mini course, we will do this just in the Pytorch, where you see that the function, the implementation is very simple. So so the only way how this function properly works if the y and y prime is always in the range from 0 to 1. And yeah, so because if you imagine the logarithm, right? The logarithm in minus would not work. This will be very bad things happening if you do that in minus. And in over 1, it's also not in the same shape. So the idea is that here in the y vector, you will have the ground truth vector. For example, the ground truth is this. That this is a gasoline car, for example. This is our ground truth vector, y. And then y prime is the predicted value that comes out from the softmax. For example, in this case, the predicted value could be something like 95% this thing, and then let's say 2% this thing, then 2% this class, or 95% petrol car, then 2% the diesel car, then 2% LPG car, then 2% the natural gas car, right? So these are the vectors there, and epsilon is something for numerical stability, which could be 1 e minus 8 or something. So that's about it. It's really simple. And then afterwards you can calculate which, if the classes match. So if this class prediction match this class prediction, this is a correct accuracy. So this means that this is correct classification. If they don't match, this is incorrect classification, and that's how we can then calculate the accuracy, right? So let's then try to implement this classification task for predicting which type of fuel uses this car. So let's see what we have here. So first of all, we need to change a little bit here. So instead of having 4 embeddings, we will have only 3 embeddings. So let's see. So here we don't need any more fuel. So I will delete that from the comment. We'll have 3-dimensional here and 3-dimensional here. And then for the outputs, of course, we need to have 4-dimensional outputs now, not 1-dimensional, because we need to predict 4 types of classes, right? Probabilities of those 4 types of classes. Then the last thing is we need also softmax. So torch and n softmax, and dimension over last dimension, which is -1, like that. So I'm adding this part of the code to the Jamboard. So these are the only few changes in the model to make that the regression type of model now is a classification type of model, where we don't predict just one output of a scalar value, but we predict the probability distribution with 4 outputs, okay? So this part of the code I think is the same. So I just dropped that on the Jamboard on the slide number 13. Now I try to run it. Okay, I think it will not work. Okay, something works, but funny, the loss function works. Why the loss function works? This is funny. Okay, I accidentally run the wrong code. If I try to run so make sure that you run the correct file. If you press on top here and run the correct file, then it will work. Oh no, I have a problem here. Oh yeah, so sorry, I have a problem with one hot encoded. So here, this is a torch function, and now I'm trying to use it as it would be the numpy function. So again, here we'll have to have the torch from numpy, and then use this y here. I will update also this on the Jamboard just in a second, but you need to fix this line. So now let's see if it's working. Okay, there is another issue. We'll check that just in a second. But this is the first problem. So first of all, we cannot use torch functions on numpy objects, and that was something that I did. So here on the slide number, which 11, I guess. Yeah, on slide number 11, I will update the code. So let me show you. So here on the slide number 11, there is a bug fix here. So okay, that's one. Let's see what else is not working. What else is not working? So the kind of dimensions are wrong, which means that I messed up something. So let's see the classes, 3 classes, labels. Oh yeah, I know where the problem is. So we just took out the fuel, but here these guys are not then in the same order. So instead, what we need to do is following. So we will take the brand car, then we will take the transmission, then we will take the dealership. So indexes of those labels, because they were in the wrong size of those indexes. So I will try to run it again. I hope now it will work. If it will work, I will drop you. Oh, okay, there's something again not working. So number of embeddings, labels, 3 labels, embeddings. What is wrong? X classes. Let me check. X classes. Okay, X classes 4. What is this? X classes. X classes 3. There should be X classes 3. Okay, fine. Let me check. So I will quickly debug, check what is wrong here. At least this line should be like that. So upper part of the code, I think, is fine, at least in some manner. So I will update that also to the Jamboard, and we'll fix the lower part of the code. So it definitely means that some embedding size is not correct. So we'll run it again. Okay, let's see what's happening here. So the X classes are, what is this? So yeah, so three classes, except, so what it means that the car brand, transmission, and dealership, right? So that's good. Then afterwards, when I get the embeddings for those 3 classes, I get 9 embeddings, which is correct. Then the X inputs are 4. Okay, here's my problem. I forgot that the price is now added as well. So here the input feature should be 4 plus 3 times 3, because 3 embeddings for 3 labels here, 3-dimensional embeddings, right? And then the 4 because I added also to the kilometers driven, to the years produced, and also to the owners. Also, I added the price. So the price is not now the output, but price is the input now for the model. So we are trying to predict which type of fuel this car uses based also on the price, not only on the on other inputs. So that's why I forgot about that part. I will add this small change to the Jamboard, slide number 13. And now this should work, but it will not work completely because the loss function is not implemented, of course. So if you see, now I added these 2 lines here on the Jamboard. Okay, now let's go back to the loss function. So the loss function here, this should be something that you can implement yourself. You should be able to implement yourself, but I will help you out. So minus torch mean of very simple loss function. I don't know what could be simpler than that. So y multiplied by, because this is not a matrix multiplication, because they are just 2 vectors and we don't want to create matrix of them. So y prim plus e minus 8, whatever. So this is our loss function. Very simple stuff. So now I try to run it. Okay, I see that I'm starting to see the loss value reducing. So I also have additional plots here, which we don't use right now. We don't use the confusion matrices, and we don't use the accuracy. And I also want you to later at the home to change the accuracy to the F1 score, which I will give you the formula. And but instead you see that the loss plots are reducing. So that's really nice. So the loss is working. So I will drop also this to the Jamboard. And now I will help you to calculate the accuracy as well. Usually I'd ask those tasks for students to do online, but otherwise we will not have enough time, probably. Or maybe I should ask you, because we still have a little bit of time, but anyways, I want you to start working also on the homework. So otherwise, because the homeworks. I think the last homework, let me check how many people submitted. So the last homework was submitted by 4 people. So really hope that people will be able to finish this course. And in general, even the live classwork last time was submitted only by 4 people. So remember that you might not pass this course if you not submitted the homeworks and the tasks of the live classroom. So anyway, here the accuracy. So the accuracy, what it means is that we have 2 vectors and we want to find where the vectors are matching with each other, right? So let's write then matching samples, which is the correct samples basically. Let's say correct class samples, correct samples, and those samples are of course those ones where they match directly by y prim, and this will give us okay, sorry, there's a problem here. Okay, let's write y prim index. So let's convert back from the one hot representation into index representation, because that will be easier to compare them. Is this the same class or not the same class? It's not about the learning now, because we already did the learning. The learning part is already done. Now we just want to see if the result is correct or not correct. So y prim index is the y prim argmax, so of dimension -1. So I don't want to have the maximum values index selected on the batch dimension, but on the class dimension. So, and then I do the same for the original input y. Now I have the indexes of the predicted and the real values. Now I compare them. Is this the same index as this the index, right? And what we will get here is the kind of vectors with true, true, false, and so on, true, and so on. So I mean, there will be in the size of batch, basically, for every sample in the batch, we will get if this is a correctly classified sample or incorrectly classified sample. Then we have, when we have these correct samples, then the easy thing what to do is to calculate them as to convert them to the kind of zeros and ones. So these will be then float correct samples, which means that I want to multiply or basically cast it from boolean to the floating point, which this will create instead 1, 1, 0, 1, and so on. So this will mean that this is a correct sample, incorrect sample, and so on. So this will be a floating point vector, and then the last thing is like trivial. It's just like np mean of the float correct samples, and now we have the accuracy calculated. So if I try to run it, we'll see what happens. If I get the accuracies increasing when I'm training, oh no, I have a problem. What is this? Okay, the problem is that I was using the numpy where I have a torch. So torch, and then what else we could do is accuracy data numpy, like that. I think now it should work. Let's see. Yeah, it seems like working. Okay, let's see what happens with the accuracy. Something is not working with the accuracy, or is maybe the plot not correctly set. The accuracy is here. Then in the plot, what we have, accuracies train, accuracies test, of the accuracies mean, something is strange here. What could be here? So let's move back to the numpy. I just don't want to spend too much time debugging it. I will just use numpy, and here I will also add data numpy numpy, like that. So that will be fine. Then for accuracies, I also want to print them, probably. Sorry for this, I will go back to that part of the code. I encourage you to also to add these lines so you can print it out to see if accuracy is actually changing. So how to do that is just to copy the same thing here, change from loss to the accuracy train, and accuracy test, right? And like that. Oops. Okay, accuracy test. Have it here, and now I move up here in the same code that I showed you how to calculate accuracy. We'll see what happens. Okay, now the accuracy is increasing, seeming. Okay, something or nothing is actually changing. Okay, it's increasing. It's very slowly increasing, but it is increasing. So now we be able to predict which type of car it is by 33% of the time, and then you can make your models more powerful so that they can predict the car type of the fuel more efficient, right? So then for the homework, you will need to calculate F1 score, you will need to do a few other changes in the model, and then you can imagine that you can make your own AI models which could predict all sorts of things regarding the prices, regarding the classes, categories, and so on. So the one thing, so I'm dropped this to the Jamboard. So if you want, after this course, to work with me with science projects, or me being your scientific supervisor for master thesis or whatever, or bachelor thesis, then you must have to finish all of these homeworks in very good way. So this is the way how you could work with me for the next phase after we finish this course. If you want just to pass this course, then you at least need to submit all of the classworks. If you will not submit the classworks, you will not pass this course. So that's it for today. I hope that this was interesting. So you already know what you can do with deep learning. As you see with the Pytorch, you can create really intelligent models. So let's meet you next week when we will look at the image classification tasks. That's it for today. Bye bye.